Hello, everyone. Graham Stevens here from KETIV. We're going to just wait a few minutes until everybody gathers, and then we'll get started. So we'll just wait one more minute to see who else wants to join, and then we'll get started. All right. Good morning. I'm Graham Stevens here from KETIV, and I'm presenting this webinar on modeling heat flow inside motors using Ansys simulations. I just wanted to inform you what's upcoming in terms of the future KVAs. On November 21st, we have 10 best practices for manufacturers coming up. And then, of course, 2 weeks from now, we have Thanksgiving, so we're not going to do a KVA. And after that is a December 5th KVA on AutoCAD Plant 3D ACC collaboration projects. If you're interested in any of these, please do scan this QR code and sign up and or contact us here at KETIV. And my screen going here. So as I said, I'm an application engineer here at KETIV, focused on Ansys products. I've got 25 years of product development, consulting, and simulation experience, and I provide application support for Ansys mechanical, thermal, high frequency, low frequency, as well as optics. I'll be presenting this webinar on thermal modeling within Ansys, especially as it's done for motors. So we're specifically focused on motors here. What I'm planning to do is to present the different heat flow packages within Ansys, and then compare these packages in terms of their workflows and some of the pros and cons of using each package, provide some customer examples with regards to motor thermal modeling, and then an extensive list of how to obtain further information and or dive into this arena so you can sort of get started effectively. So within the Ansys universe, there are 5 heat flow packages that are applicable to motors. They are Icepak, Fluent, Ansys Mechanical, MotorCAD, and Thermal Desktop. Thermal Desktop is a new acquisition of Ansys as of roughly a year ago, so it's just getting integrated into the fold, but it's definitely part of the puzzle. I'll be just describing each of these in turn in the next few slides. So Icepak is a CFD package that's been designed for electronic applications in particular. So its special purpose is to look at these um, uh, electronic boxes where you might have electronic components, you might have some heat sinks, you might have some fans, you might have water cooling, and it's designed to analyze the convection and conduction and radiation inside these packages, and look at, is my cooling, the method I'm using for cooling all of my PCBs and chips adequate or not. So it predicts airflow, temperature, heat transfer in IC packages, PCBs, electronic assemblies, power electronics, anything to do with electronics, and it's kind of slated towards that application. Icepak also comes in two flavors. It comes in an AEDT flavor, which is integrated with all the other electronic applications within the Ansys universe, and it's accessed through the electronics desktop. And then there's an older version of Icepak that has an older interface. It's more icon-based and accessed through Workbench. Icepak has been around for 20 plus years, and so this is an older way of doing things. At this point, most of the, or all of the functionality of Classic has been ported over into AEDT. So for new users, we definitely advocate jumping into the AEDT version, but the Classic is available if you're used to the older way. And so the second heat flow package within the Ansys universe is called Fluent. And both Fluent and Icepak use the Green-Gauss finite volume method of calculating fluid flow and doing heat transfer relative to fluids. And in that formulation, we're solving the Navier-Stokes equations for the transport of momentum, mass, and energy when calculating laminar flow. With turbulent flow, there are additional transport equations that are solved, kind of listed here, 0, 1 equation, 2 equation, a bunch of different types of models. But essentially, we're taking the fluid volume, breaking it up into little tiny bits, and then analyzing each volume using this solution process that's on the right. And so Icepak is equivalent to Fluent, but it's been designed with sort of electronics engineers in mind in terms of interface. So it's a little bit easier for electronics engineers to use as opposed to a fluids engineer. It's been sort of simplified essentially, but you get the same functionality. Fluent has more capability. It can do two-phase flow and a bunch of other maybe more exotic or more complicated tasks. But Icepak is virtually equivalent in terms of how things are done. The third package I wanted to introduce is Ansys Mechanical. And you can sort of see in this model, this particular engine block has been chopped into little tiny bits called finite elements. And so it's a finite element analysis simulation where the stress equations and thermal flow equations are solved kind of element to element. And typically it's focused on the solids as opposed to fluids. So the solids are modeled here. It can handle fluids if you sort of approximate them as solids. And the only other limitation is that typically for convection, you would handle that within mechanical as a heat transfer coefficient applied to a surface as opposed to modeling convection on its own. And so essentially for conduction problems, convection with heat transfer coefficients and with radiation, you can do those sorts of models within mechanical. So it's a little bit more limited in terms of the physics it can do. But it also makes it really easy then to get mechanical properties. So if you have thermal stress and you're trying to analyze that, mechanical is the place to do that. So you don't have to transfer your model to fluid, transfer the convection specific model from Fluent, say, to mechanical, to then look at the mechanical properties of the system, you can just do it right there. So the fourth package I wanted to introduce is Ansys Motor-CAD. Motor-CAD is a design tool designed specifically for motors, in particular motor types, permanent magnets, induction motors, etc. And it's an expert tool where expert designers of these motors have put in a lot of effort and time looking at the governing equations. So it's more analytical based, but it's also supplemented with 2D FEA calculations. And it really combines a lot of different aspects of doing a motor. So it looks at both the magnetics, you can sort of see here in the EMAG portion. It has a thermal design part of the system that models advanced cooling systems. It also looks at mechanical stress and displacement, and it can look at duty cycles and efficiency mapping in the lab module. So it has 4 different modules looking at motors in different aspects. It runs a lot faster, so typically 5-10 minutes for an analysis rather than hours that you might do for finite elements or Fluent. And so it's slightly less accurate, but it's also very fast. So it's useful at the design stage and getting you close to the design you want, and then you go back to mechanical and Fluent to tweak the design and get your final iterations and designs complete with more accuracy as you go. And so on the thermal side, well, we'll discuss the thermal side now. So within the thermal side of MotorCAD, what they've done is they've taken they've created a resistance network of a typical motor. So looking at the heat produced from the magnets, and then how does that flow to the rest of the system? It might be radiating into the airspace that the magnets are in. It might be touching the rotor. It might be touching the stator, whatever it is. And they've created a resistance model and then looked at actual data for induction motors for permanent magnets and calibrated that resistance model back and forth so that you've got a really good representation that's battle tested against what reality is to approximate what the thermal behavior of these motors is. And because it's a resistance network, it's sort of a 1D equation type of analysis. And again, it runs much faster. And we can also do some transient solutions as well in terms of looking at transient behavior. We can get radial temperature distributions, as you can see here. We can evaluate different types of cooling methodologies that are part of the program. So oil spray, etc. There's a bunch of different types. And so this is sort of kind of the place to start relative to doing motor cooling and thermal. We can also take this model from MotorCAD once we have it and then export that to Maxwell and get more accurate on the EM side. We can export it to Fluent to get more accurate on the fluid side or mechanical. You can also export this thermal network into thermal desktop, which we'll discuss in a minute as well. So Thermal Desktop is a new Ansys acquisition. It was originally created for the space industry, or that's sort of its start, and looking at radiation in outer space and calculating kind of 1D equations and trying to make that fast and easy, and then has moved towards simple heat exchangers, and these sort of resistance networks for modeling things sort of at the system level very quickly for early design evaluation, rapid design changes. So again, it's used at the early stage. It's been more focused on sort of the space industry applications and some of these heat exchangers as opposed to motors. but there are some motor applications as well. So its basis is it is a 0D or 1D lump parameter network simulation. So it solves in minutes and seconds. You can sort of see here compared to the days or weeks or hours for computation time here in terms of Fluent and mechanical Icepak. So it's used at the early stages, but it's also less accurate. Okay. So that's all of the different packages. And now we'll start talking about some of the workflows. So for motor applications and heat transfer, you typically want to start with this MotorCAD workflow. So we start with MotorCAD itself and look at the design from an electromagnetics perspective, an initial thermal resistance model, maybe mechanical. You can look at NVH. You can also look at efficiency plots and get sort of a system picture as well. You might then take that model and port it into Maxwell. So you dial in on the electromagnetic portion of the system where we're looking at 3D effects, edge effects, fringe effects a little bit more effectively in Maxwell. You can also pass that model into mechanical or Fluent and do, or Icepak and do CFD modeling and or more mechanical modeling. And we can take the MotorCAD model and pass it up to the system level where we might look at system validation or operation in terms of integrating it with electronics. And so this kind of overview of this workflow is typically what Ansys recommends relative to motors and looking at motors thermally. Within any one of these packages, and I'm talking now about more of the finite element packages, so within mechanical, within Fluent, within Icepak, your typical simulation workflow will look something like this, where you define the materials, you do the geometry prep, you then mesh the model, you do the simulation setup, so you tell it what the loads are relative to thermal loads, what temperatures are involved, where those temperatures are applied. You then press the go button and do the simulation, and then you get a bunch of results and output those and maybe compare and report. So this is sort of your typical workflow for a finite element analysis or finite volume analysis. Within the MotorCAD universe, if you're sending the model to Fluent or to mechanical, a lot of the material definition geometry preparation is already done. And then you might modify from there if you're doing tweaking of the design, etc. So this is typically how the workflow would be done within those finite elements packages. Thermal Desktop has a slightly different workflow. It starts with your discovery, space claim, or CAD geometry and or design concepts. And then within the Thermal Desktop package, there are predefined shapes and predefined flow networks you can do. And you can create finite element mesh as well. So it can integrate 1D, 2D finite elements and solutions, and then get solutions here in Thermal Desktop. For thermal calculations here, again, I would advocate starting with MotorCAD, and then you can take the MotorCAD thermal network and transfer it wholesale to Thermal Desktop and then modify from there. So if you're looking for sort of a starting point on, I need a thermal model for a motor, it's embedded within MotorCAD, and then you can pull it into Thermal Desktop and change it, work it from there if you like. And then again, on the system simulation side, when we're starting to think about system simulations, we can get an electrical model, so an ECE, electromagnetic DX flux linkage model. We can pull that into Explorer, Simplorer. We've got efficiency loss maps, the thermal model export I was just talking about in terms of resistance networks. We can co-simulate with Fluent. And then also create reduced order models in Fluent and pull those into the system simulations. So all sorts of different possibilities when we're talking about the system level and getting a good feel for how your motor is going to act at the system level. So then, so those are all the different workflows associated with thermal and motors. And this is just a very bird's eye view of calculations or comparison of these different packages. So the other thing I want to emphasize here is it really depends what your basis point is in terms of package learnings. So if you already know Fluent, it's probably going to be easier and faster for you to just take the model from MotorCAD and jump right into Fluent or start with Fluent. If you know mechanical, again, kind of start with what you know and go from there. And then if you know Icepak instead, again, transfer things into Icepak rather than working in Fluent because that's what you know. It's faster, easier, better. So there's a training aspect to this as well in terms of what packages you know. But in general, the MotorCAD package is a standalone package. It's basically sort of throw a bunch of input. You have a list of templates and then you have inputs. So it's basically filling out the inputs, what materials, how big is it, what does my stator and rotor look like internally, what do the windings look like. So you define the motor there, and then that defines your geometry, your initial geometry, and then you can send that off to mechanical or Fluent or Icepak. A kind of minor secondary wrinkle, Ansys has two different GUIs, I guess you call them, or where you have the electronics GUI is the Ansys electronics desktop, and on the mechanical side, it's Ansys Workbench. All of these packages are integrated in, well, most of these packages are integrated within Workbench. Some of them are integrated within AEDT. That's what this AEDT is, Ansys Electronic Desktop. So there is a version of Ansys Mechanical within the AEDT framework. So you can work and do some mechanical simulations within AEDT. And again, that's sort of slated towards electronics engineers that don't want to have to learn mechanical as much, and they just want to do a brief analysis there. Similar to Icepak, where they don't want to learn Fluent in all its glory. So they start with Icepak that's structured for their use. So again, relative to, it just sort of depends if you're used to the Workbench environment versus the AT&DT environment, that can inform which kind of package you might lean towards as well. But MotorCAD can be exported to either. So this is just, again, sort of a visualization of when we start looking at multiphysics, and now we're started looking at, well, for a motor, we have the electromagnetics, and how does that influence by temperature? So the magnets are going to lose force as they go up to temperature or not, or what's happening there. And so typically we want to couple these analyses. So we have Maxwell that's focused on electromagnetics, coupled with Fluent or coupled with mechanical. And within the Workbench environment, there's this system coupling setup that allows you to merge analyses, take the resulting thermal field from a thermal analysis and send it to structural, so that you can then find out how did my model warp because of thermal stresses. Similarly, for Maxwell, you might be passing electromagnetic information back and forth. So MotorCAD will feed Thermal Desktop, it'll feed Maxwell, it will feed mechanical. So that's sort of how these are linked together when you get to the multiphysics side. And then Icepak within the ADT environment also has its own links and ways of doing these sorts of flows. In addition, there's an EM to Icepak ACT, so a little module to make some of these electromagnetic fields pass to Icepak and back and forth coupled analyses easier as well. And so, of course, when we're thinking about multiphysics, we want to start thinking about what is changing, and is it changing a lot or a little to the point where I need to do system coupling. So relative to motors, typically we have heat, and the heat is affecting how our magnets operate. And so if we know our motor is going from 20 degrees C all the way up to 100 degrees C, or how is that going to impact the motor? If the change in properties of the magnet, this is resistivity here in terms of copper and joule heating, but it could be your magnetic properties. If those are changing a lot in the temperature range that I'm doing, then a coupled analysis is the way to go. And then you can also think about, am I doing a one-way transfer or a two-way transfer? So I can take the temperature profile and just not worry so much about how much the, say, conductivity of copper is changing, or how are my magnetic properties changing, and just get a one-way answer. Or I can feed that information back and get a two-way answer, which is much more accurate, but of course costs a little bit more in terms of time and calculation. And typically what you'll always want to do is run the models separately, make sure you thoroughly understand the physics and some of what's going on there, then do a one-way coupling, then do a two-way coupling, and kind of build up to a two-way coupling so that you can isolate the impacts of each of those things. When we're also thinking about doing motor analysis and thermal analysis, typically you have a lot of trade-offs between the magnetic properties and the magnetic design and the thermal design and, say, the mechanical design, or looking at efficiency in terms of my electronics and what's happening there. And so there's a lot of different, huge number of different variables that will affect your design and your overall efficiency, and certainly trade-offs between these variables. And so when you're contemplating doing that sort of analysis and looking at these trade-offs, we very much advocate going back and forth and using OptiSlang, because it's designed for exactly this task of, I have more than 10 variables and I'm trying to look at this design space and get a better feel and optimize. And it will, it's very up to date, including AI algorithms, will speed up this design optimization task quite a lot, and especially with how fast MotorCAD works in terms of being sort of a 5-minute, 10-minute analysis, you can really optimize very effectively using it. So we definitely advocate jumping into the OptiSlang space if that's what you're wanting to do. So just a couple of examples here. So this is a traction motor design optimization, again, sort of illustrating that OptiSlang variations, where thermal was looked at, magnetic performance, the efficiency map, stress and strain, eigenmodes, all of these different factors were optimized for structural, electromagnetics, thermal, to get to the best efficiency, weight, durability, NVH, noise, and using this kind of methodology reduced our, increased our efficiency, reduced weight. We reduced the amount of magnet that needed to be used, and of course the NDFE magnets are very expensive, and made it quieter, and also reduced the cycle times in terms of product development. So this can save you a huge amount of time, as well as getting better performance. So just again, some examples. So Lucid Motors looked at their induction motors on the thermal side. So they were looking at loss mapping in Fluent and and they were doing multi-phase oil model here. So they had to use Fluent for that. They'd use the CHT model for solids and water jacket fluids, etc. So a lot of detailed modeling and optimization. Schaeffler is a German company, German manufacturer of components, did this sort of optimization on their motors, looking at optimizing magnetic volume and reducing costs. And then, of course, Nissan Leaf did sort of the same thing, where they were looking at the magnet, designing the magnets, torque ripple, efficiency, all sorts of different factors in terms of the vehicle as a whole. So we can get out to the system level, as well as diving directly into sort of the details of the magnet design. So when you're getting started in this kind of analyses, these are sort of we recommend jumping into the Ansys Learning Hub. If you don't have access to the Ansys Learning Hub, please just reach out to us here at support@ketiv.com so we can get you that. Thermal management learning room within the Ansys Learning Hub is sort of one key place to start. If you're on the electronics side, there's an electric machines area, which also are sort of the two large bucket areas in terms of getting started on these analyses. And we definitely advocate sort of jumping into one solver and one thing first, and then going to the next, and then eventually adding into multiphysics, where you start combining some of these things. So you might want to get started in MotorCAD and get your initial designs there, then think about, well, okay, do I need to jump into magnetics and then do Maxwell? Do I need to jump into Fluent and then do Fluent? In terms of more complicated, learn Fluent, then combine the two. And again, we're happy to help in any way needed in terms of that. Within the Ansys Learning Hub, there are a couple of workshops here that are relevant to motors. The electric machines thermal management in Ansys Fluent has quite a few courses. There's this anatrizing thermal conductivity for electric motor coil windings workshop, etc. And then also within the Ansys Resource Center, with this link, there are a number of webinars that we wanted to draw your attention to that jump into, how to do these different types of simulations, showing the different workflows and so forth. So looking at cooling strategies, thermal management solutions, system level performance, optimization, etc. Some other additional resources are, of course, YouTube. There's a how-to channel on YouTube that walks you through how to do these different analyses. And then on the innovation space, there's a bunch of free courses there as well that sort of cover the basics of heat transfer and electromagnetics and motors and so forth. And then, of course, please do reach out to support@ketiv.com. We're here to help guide you through all these different resources to get you up to speed as fast as possible. So please do keep us in mind as you're getting started, and if you run into any issues whatsoever. And then I just wanted to mention here as well that KETIV provides simulation services in the mechanical, fluids, electronics realms. So if you are not familiar with, say, MotorCAD and OptiSlang, or you're not familiar with fluids as it applies to a motor problem and don't have that capability in-house, KETIV can possibly provide that capability for you and be part of your team. And we also do these simulation services as a training method. So we might start by saying, okay, we'll do your first fluid flow as you transfer your electromagnetics out of Maxwell as an example, and to train you in doing that sort of analysis. So keep us in mind on the training side as well. And with that, I am finished. I wanted to kind of take a break now and just ask if anybody's got any questions. Love to take those on as well. Kind of throw them into the chat. All right, and barring any questions, we will stop. Thank you so much. Really appreciate your time, and happy computing and diving into this thermal systems relative to motors. Take care.